Hi, this is Mark Weitzman. Welcome back to our sixth video in this partial differential equations series. Today I'd like to do problem 8.4 from Mathews and Walker. And the problem reads, find the three lowest eigenstates of the Schrödinger equation for a particle confined in a cylindrical box of radius a and height h. And the Schrödinger equation in that case is minus h bar squared over 2m. For those who aren't physicists, h bar is Planck's constant over 2 pi, and physicists always call it h bar and write it as h bar. Del squared psi equal E psi. We're a free particle, so there's no potential. And so we have a cylindrical box. And the height is h. So don't confuse that with Planck's constant, which is h bar. And the radius is a. And so for our coordinate axes, we're going to use cylindrical coordinates. And this is y, this is x, and this is z. And, particle P, point P, will project down to the xy plane. This will be r. This angle here will be phi. And the height will be z. Okay, so that's our coordinate system. And our boundary conditions for this problem are that psi has to be 0 on the boundary of the cylinder. So psi equals 0 when r equals a, or z equals 0, or z equal h. Okay, so as I said, we're going to use cylindrical polar coordinates. R, comma, phi, comma, z. I know in one of the earlier videos I used rho. I'm not going to use rho here. I'll use it later as a scale change, but I'm going to use r. And if you look up in those things for the Laplacian and cylindrical coordinates, we're going to end up getting this equation. And we're going to substitute our usual product of wave functions. Okay, I'll put a line for the z, make a capital Z. So we do our usual strategy. We substitute this, and we divide. And we're led to this equation. Now, looking at this equation, we can see that this is the only term that involves z. So we would separate that out, and that would be equal to a constant. And we're very familiar with this equation and the solution. I'm just going to write it down right off the bat. No fooling around anymore. Z is equal to sine k pi little z over h. Remember, h is the height. So any sine function will clearly satisfy this thing of the second derivative being negative itself, but we also want to satisfy the boundary condition. So k is a I should say minus k pi over h squared ends up being a separation constant. And this thing automatically satisfies the boundary condition. When we put z equals 0, it's 0, and when we put z equal h, we get sine k pi, and so I'll put k as an integer, and sine of an integer times pi is 0. So we've got part of it satisfies boundary condition. At z equals 0 and z equal h. Okay. Now we substitute this into there, and we're going to end up getting I'll check this after I write it down. Obviously, I multiply by r squared. This should be a minus here, I believe. R squared times minus k pi over h squared. Okay. I'm going to just change that to a minus sign there. Plus 2 me r squared over h bar squared equals 0. And now we notice the same thing again. This term depends only on phi. It's the same exact equation. This time I'm going to use a little different solution. I'm just going to use like the quantum mechanical basis, the angular momentum basis. Phi equal e to the im phi, and m is an integer. So the reason why we're using this thing is the only thing we have to satisfy here is continuity. We have to have the same thing at 0. At phi equals 0, and we have to have the same thing at phi equal 2 pi. Otherwise, there's no other condition we have to satisfy. The only way we can satisfy that is m is an integer. And this could be like plus or minus, 0, comma, plus or minus 1, comma, dot, dot, dot. Okay. So now when we substitute this back in here and multiply by r and do some other, split this up again, we end up with this equation. R squared d2r dr2 plus r dr plus, gonna have this whole thing in here is going to multiply by r is equal to 0, and in here we're going to have r squared 2me over h bar squared minus k pi over h squared minus m squared. Okay. So you can see I have the minus r squared k pi over h squared. I have the 2me r squared over h bar squared. That's good. this thing, when I substitute it in there, just gives me a minus m squared. That's cool. And then we multiplied all of these by the r, and when I take the second derivative, I get the r squared d2r, and then when I take the first derivative, I just get, so it looks good. Okay, so now, if you look at this equation, you can sort of see right away, if you're a theoretical physicist at least, you see right away you're headed to its Bessel's equation. But to do it slowly, we'll do the substitution, r equal alpha times rho, and then the equation becomes rho squared d2r d rho 2 plus rho dr d rho plus rho squared alpha squared times 2me over h bar squared minus k pi over h squared. By the way, I left out something in this problem which was important, namely that when a is approximately equal to h. We'll use that in a second. But when I first saw that in the problem, I said, well, what do they mean by approximately? Is it exactly? Is it close? You'll see it doesn't matter, but it's approximately. Let me go back to this equation. Then I have minus m squared r equals 0. Now if we just set alpha equal to 2me over h bar squared minus k pi over h squared to the minus 1/2, then this squared will cancel this factor, and we'll be left with rho squared d2r d rho 2 plus rho dr d rho plus rho squared minus m squared r equals 0. And this is a Bessel equation. And it has a second order. It has two linearly independent solutions. But again, we're only interested in the regular solution at r equal rho equals 0. And that solution is what's called a Bessel function of the first kind. And the order m is the parameter in here, and that determines the order of the Bessel function. So we can write down our solution as r is equal to jm rho, which is equal to jm. Now we're going to substitute rho equal r over alpha. So it's jm r times the square root 2me h bar squared minus k pi over h squared. Okay. Now the only boundary condition we have to satisfy is that r at r equal a equals 0. So this requires that a times the square root 2me over h bar squared minus k pi over h squared. This has to be equal to, we'll just call it zmn, which is the nth root of jm. Down here I have the roots, or the zeros, of jm, zmn. And so I have n equal 1, 2, 3 over here, and m equals 0, 1, 2 down here. I just copied this table out of Jackson Classical Electrodynamics, second edition. You can go online and get the roots. You can use software. You can look in a book. So using this, now squaring this equation, we get 2me over h bar squared minus k pi over h squared equals zmn squared over a squared. And this just implies that E is equal to h bar squared over 2m times k pi over h squared plus zmn over a squared. And now we use the h is approximately equal to a to simplify this. So now we use this. This implies E equal to h bar squared over 2m a squared times k pi squared plus zmn squared. And this is in a sense our solution. This combination over here, those who have done quantum mechanics will recognize it right away. So, and this is the sort of integer quantization conditions. So we want the three lowest eigenvalues, and the easiest thing to do is to do trial and error and find out, substituting in this. You find out pretty quickly that this factor over here for m equals 0, k equal 1, n equal 1, that's the lowest, it's 15.65. For m equal 1, k equal 1, n equal 1, it's 24.55. And finally for m equal 2, k equal 1, n equal 1, it's 36.25. And you can verify that the other combinations are much bigger than all these three. So thank you for watching this video, and I'll return for one more problem in Mathews and Walker, and that will probably do it for now on PDEs. Thank you very much. Bye bye.